Hi there, general physics. Let's talk math. Let's talk free body diagrams and math. This particular video for the next several minutes is going to go over the basics of math, figuring out the vectors. It's going to look at some of the newer situations where we have to employ some geometry and definitely some trigonometry in order to solve those questions. No worries, lots of practice ahead. All right, but if you either were lost during class time or you're absent for whatever reason while we're doing this, this is a critical video for you to watch with your workbook, with a calculator. Be prepared to pause here and there, right? And try some things on your own. Just don't sit with your earbuds in and just, half attend. This is an important one, you guys. All right, so if you need to take a break, pause me, go back, get a drink of water, eat a cookie, whatever, come back. All right, you need this one. You need this one. We're going to be using this stuff for a good long time. All right, so let's get going. As you can see, I've got the workbook up here, and this is page 43 of your workbook. So if you're not there, get yourself there. And I'm going to use these examples to kind of get us started. All right, so we're going to start off with some straightforward, plain, simple stuff. And actually, I'm going to grab this because I can put it over parts of my Chromebook so I don't accidentally turn things off. That's always important. Okay, let's start with number 2. If I were to say to you for number 2, okay, here's my free body diagram. The mass, I'm going to actually change colors here. I'll put in the black. Let's say the mass of my object is 10 kilograms. And I want to know the magnitude. Now, here's a word that always throws everybody. Magnitude. You know what I mean when I say magnitude? I mean number. Find the number. Find the calculation. Give me the value of both of these forces, gravity and normal force. So how might I do that? Well, I would hope right away you'd say, I know how to find FG. All I need to do to find FG is use that formula, and I know that little g is 9.81. Whether you want to say meters per second squared or newtons per kilogram, both are good. Oh, my kilogram went right off the page. All right, so in my head, because I can do math in my head a little, and I did strategically pick the number 10, right? I know that FG is going to be 98.1 newtons, and because I have balanced forces, we are moving with a constant speed with no friction, we are looking at 98.1 newtons for my normal force. They must match, right? This box is not levitating off the ground, getting faster, heading up toward the sky. It's not sinking through the earth, crashing towards the core of the earth. It's just on the floor. These are balanced forces. These match. Okay. Easy peasy, right? Right. Well, what we ended up doing was applying that to some that perhaps had, let me find a few here. Actually, let's try the next page over. Okay. Let's focus in on number 11. All right, now let's assume, I'm going to change it just slightly. Right here, we assumed there was no friction on the floor. But let's say we do have friction, also caused by the floor. And we had the same exact issue, right? Let's say the mass is 10 kilograms, but let's say I give you a 50 Newton tension, right? And I asked you to solve for the forces there as well. Same thing, right? You'd find FG. We'd get the same number that we had the last time for, newtons, for exactly the same reasons as before. The normal force would also match for the exact same reasons as before. And then now you would have left and right forces. Your tension would be 50. And if we are moving with constant velocity across the floor, which I would have to tell you, failed, sorry. All right, there we go. Constant velocity across the floor. Then you would also say, well, the friction must be 50 newtons. Okay, fair enough. That makes it kind of easy. All right, what about stuff that gets a little trickier? For example, what about like number 7? This object suspended from the ceiling. Like that doesn't look quite the same. Like things are sideways. How do I deal with that? Or number 8, what do I do there? Right? We've got that one tension going this way, and then there's another one going straight across. Like, how does that work? I'm so glad you asked. We are going to take a look at the procedures that we use when things don't line up so easily, right? The stuff that's left, right, up, down, super straightforward, right? Especially if we have balanced forces, especially if we're talking about an object that is either at rest or it's moving, but it's moving with constant velocity. So how do I deal with that? Well, I want to find a blank page of notes. I want to say about on page 36. You should be okay, but I know this is an old spot here. I'm going to grab just the first blank page I can find, which is here, page 49. As you can see, I've used this workbook on these recordings for a year, so I'm running out of space. So please don't go to page 49. Please go around page 36, 37 of your workbook for this. Okay, so let's take some notes. Let's take some quick notes. Now, they are not called FBD math problems in like a textbook, right? We're talking about balanced force problems, whatever. But basically, we're drawing these FBDs, and we need to figure out the value, the magnitude. There's that word again, magnitude. We want to know the numbers for all the arrows. So how do we do that? Well, as you can see, the very first thing that we do every single time is draw an FBD, right? I mean, now we had those drawn already, but you need to draw that. You need to know what arrows you're dealing with. The second thing we always end up doing right away is to solve for what we can. I'll say solve for the obvious. And what's obvious? Well, usually FG is pretty obvious. Maybe, and you'll see why soon, maybe normal force is obvious. Maybe tension is obvious. Maybe friction is obvious, but maybe they're not. That just depends. Gravity is usually my most obvious ones. Now, what about the stuff that is not so obvious? What do we do there? Well, what we're going to do next, and this is new, I've been spelling this wrong for a day and a half. All right, diagonal. All right, forces. All right, so actually I'm going to take that and I'm going to put that in parentheses instead. So we're going to look for diagonal forces, and we are going to break them up into triangles, or really what we're going to do is we're going to find component vectors, and I'll explain what that means in a minute. Okay, but this is new. This is where we're going to focus a lot of our energy during this lesson. So that's where, if you need a cookie, go get one, because you're going to need it. All right, the final step, once you do all this work with diagonals and triangles and stuff, you're going to use the basic premise that we mentioned about balanced forces, that left has to equal the right, the forces pointing left have to equal the forces pointing right, the forces pointing up have to equal the forces pointing down. And you're going to use those premises. Once you're done with the diagonal stuff, then you're going to look at the whole picture and say, okay, everything that points up, what is it? Everything that points down, what is that? Set them equal. What's pointing to the left? What's pointing to the right? Set them equal. And solve for your missing pieces. That's the game plan. Now, if you're saying to yourself, yeah, but that's not a formula, Mrs. Grady, like that is not something I can use every single time. You're right, because you know why? Every free body diagram is a little bit different, and we have to use our noggins and figure out what is going on in each specific situation. So this is the most generic game plan I can give you. All right, you cannot come up with a set formula for this because every situation is different. What I can give you, and what physics typically looks like, is we give you the tools to put in the toolbox, and then you can pull them out as necessary and use them as needed in the right spot. That's the game plan. So if you were hoping for an easy peasy formula that you could use for the whole shebang, I'm sorry, it's just not there. But this is a strategy that we can use effectively to solve really all sorts of problems. Now, I don't know if I'm going to have enough room, but we're going to try. Dang it, we are going to try. Let me put my glasses back on so we can see what we're doing. Okay, so I am going to hopefully go back there. All right, let's give it a shot. We'll see. I might have to, well, we'll make sure. We'll see if I might bleed up a little bit in my notes here. Just an FYI. We're going to start with number 7. All right, let's take a look at what's happening there with good old number 7. All right, again, let's say that our mass is 10 kilograms. That way we don't need to do a whole lot of extra fancy pants stuff to find our gravity. And let's figure this up a little. Let's figure that the angle that I have there with the ceiling, I don't know, let's say it's 40 degrees. This is the number I used in class. So 40-degree angle. It's a little bit bigger and easier to read. There we go. All right, so 40-degree angle. If my mass is 10 kilograms and we do the same stuff we did before, we would know that the gravity is 98.1 newtons. Okay, now let's take a look at the tensions in this rope. If each of these angles is 40 degrees to the ceiling, that tells me without any other work that the tension in each of these ropes, tension number 1, tension number 2, they are identical. Why? Because my angle is the same. If my angles are different, the tensions will not be the same. But we have to divide things evenly. Now, before you say, well, I'll just cut 98.1 in half, and that's the answer to my question. No, it's not. Those ropes are not straight up. Those ropes are tilted. All right, so you can't take 98.1, let's say it's 100, right? Round it. And you say, oh, well, each one's 50, right? No, if they were like this, it would be. But since they're like this, they're not 50. You have to do a little trigonometry here. All right, you notice you have things on a diagonal. So nothing points straight up from that diagonal. Nothing points directly left or right from that diagonal. So we need to make some triangles. That's the geometry and the trigonometry piece of this. So first, let's start with our diagram. I'm going to do this in red, and you could do it on the inside of that triangle piece. I'm going to work to the outside because I think it's easier to see. Can you see that? All right, see what I did there? Now, this diagonal, this purple diagonal, it is going, even if I look on the screen, let me double check. Yep, it is going upward and is going rightward. That's how I know that these arrows must be to the right and up. Don't draw little lines, draw arrows. The arrows matter, okay? They tell you the direction of things. And that's critical in these problems. So don't be lazy, don't draw sticks, draw arrows. All right, this particular purple arrow here on the left is going upward and to the left. So I must have a left arrow and an upward arrow. Okay? Geometry, my friend, geometry. If this is a 40-degree angle here by alternate interior angles, so is that. Now, if you want to do geometry and say this angle must be 50 and work with that angle, you'll still get the right answer as long as you set up the trigonometry correctly. So if you're looking at it a little bit differently and like, oh, that's 90 degree and let me do this, that's okay. But set up the trig properly when we get to the trig part. Okay, so just watch out for that. Okay, so this is going to be a 40-degree angle. The same thing's going to happen here, 40-degree angle. This is going to help us out. Now I'm going to, I don't know if it's going to let me erase this. Oh, it did give me a little more room. Excellent. Okay, let's try that again. So let's look at this triangle. I'm just going to redraw it over here. This is my right side. And let's remember a few things. All right, this is my hypotenuse. Hopefully we recognize that. If you remember this fun thing, remember that from math class? So, ka, toa, right? And what does it mean? It means that the sine of the angle equals the opposite over the hypotenuse, right? Sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. Tangent equals opposite over adjacent. That's going to come in handy. We're going to use those. All right, so if this is my hypotenuse, how do you identify adjacent and opposite? It has to do with where the angle is located. Okay, so if I'm working with the 40-degree angle, this is my opposite side. If I was working with the upper angle up here, my opposite side would be over here. See where my dots are going? But we're working with the 40-degree angle. So my opposite side is over here. This is my adjacent side. Now, when I define, like this is my tension. This is what I ultimately would like to figure out. I'm going to give names besides opposite and adjacent here. Now, honestly, you can call these arrows whatever you want. You can call them, Fred, Nathan. I don't know. You give them really fun names. But typically what I do is say this is the Y component of the tension because it's vertical. This is the X component of the tension because it's horizontal. Okay? Now, because I know both of these triangles are identical, they're going in opposite ways, I have TX and TY over here as well. They're the same. They've got to be the same because my angle is the same. Now, according to up equals down and left equals right, let's consider that both of my TX's, that's left and right, that's got to be the same. That's actually kind of boring. I have nothing. I have no idea what TX is, and I just know that I have two of exactly the same thing, so good luck. But let's look at up and down. This is where it gets a little interesting, right? I have two Y components that are pointing straight up, TY and another TY, which is why I wrote it twice. And I have something pointing straight down, and that is FG. That's a little more interesting because I know the value of FG. So if FG, oops, sorry, that's supposed to be an equal sign. My bad. All right, so let's fix this. 2TY equals 98.1 newtons. Well, I could figure out TY in a hot minute now. It's going to be right around 50. I think it's 49 point something. So let's just do some math. 49.05. So I'm just going to round that. I'm going to round it to 49. What's really cool about that is now I know the value of part of my triangle, right? This is going to be 49. And it's the same on the other side. I just only have space for one thing. So, okay, TY is 49, and I know my angle of 40 degrees. If you remember back from trig, and maybe you don't because, this was the end of the year and the quarantine and all the nonsense, right? But if you know one side and an angle, you can find everything else out about that triangle. That's the cool part of trigonometry. That's where the sine, the cosine, the Pythagorean theorem, all this cool stuff comes into play. So let's look at what we know. We know the opposite side. We know the angle. We want to know the hypotenuse because I want to know the tension in those ropes. So when I look at my identities, my trig identities, then I know that I want to use this one. I want to use sine because the opposite over the hypotenuse is the sine of the angle. So now I have two of the three pieces there. I can figure out the hypotenuse from that. So let's set it up, okay? I'm going to change colors just so that it's a little bit easier to see in all this mess. All right, but let's do the math here. Sine of 40 degrees equals TY over T, well, FT. Right, we're calling it FT. So I've got those. Now, I need to get rid of the bottom of this fraction, right? Because what's going to happen is I'm going to write this in. I'm going to say 49 newtons over FT. Right? Math mistake. Every time practically. Good Lord, take the fraction apart because the fractions are what mess you up. All right, I want to get rid of FT in the bottom. What do? We multiply both sides by FT. This is starting to sound suspiciously like math class, and you would be right because we're doing the exact same thing. So FT times the sine of 40 degrees equals 49 newtons. Divide both sides by the sine of 40, just like in math class. And again, I'm running out of room, so I'll put it over here. FT equals 49 newtons divided by the sine of 40. Now, I'm going to do this in my calculator and just write an answer down. If, for some reason, you do not get the same answer as me, I want you to pause this and double check. If you don't get about 76 newtons, I mean, if you get 76.02, okay, that's rounding. But if you get like 38, double check your calculator and make sure you are not in radians. You need to be in degrees. Degrees for your angle. All right, so 76 newtons. That tells me that this is 76 and this is 76 as well. Okay, so let's think about what we know here. And again, I know how busy this is becoming. I'm so sorry. I just don't have a ton of space with which to work. I think what I'll do, 49 and 76, I think I can remember that. Let me go back to my other, nope. Let me go back to where I was. Here we go. And redraw, just with the final answers in there. What we are saying is that we had what, 98 newtons this way. This was gravity. Shoot, I'm starting to forget. 76? I think it was 76. 76 newtons this way, 76 newtons over here, right, with my 40-degree angle. That might surprise you because there's no clear mathematical relationship just out of the gate, like something easy that you can see. They don't match. They're not all 98. They're not halves, obviously not. Okay, again, it comes down to your trigonometry. It comes down to your trigonometry, so it's really critical that you do that. But let's look and see what we did. We drew the FBD. We did that already. Solved for the obvious, which was FG. And then we made the diagonal forces into triangles. And then we used the pieces of the triangle, the up and the down, to figure out the value of the y components, that they were each half of that 98, right? So half of that was like 49. And then we used the trigonometry to figure out the piece that we needed, the hypotenuse, the tension, okay? This type of relationship, we're going to see this over and over and over again. All right, now I don't have a lot of time left, so I'm going to whip through another problem. All right, so what I'm going to say at some point during this problem is take it and pause it, and then try it on your own and come back and double check the answer. All right, so let's see. Let me go back to where we were. Okay, we were about there. And let me find one. I think it's on this page. Here we go. Let's look at number 12. Let's look at number 12. I'm going to put friction in here, because why not? All right, so what I'm going to say, we'll say 98.1 here for this one as well, 98.1. And we're going to say this is 100 newtons, and we'll make it a 30-degree angle. 30-degree angle. Okay. So let's begin. I know that you probably right away want to put 98.1 on the normal force. I'm going to say, hang on to your hats, people. Don't do that right away. Let's work on that triangle. Okay, so I want you to pause. I want you to pause and draw the components. All right, so pause the tape. All right, hopefully you're back and you drew the pieces of that triangle. So here's what should be on your drawing. You should have two arrows that look like that. Okay. Now, once you've got that, I'm going to use trigonometry, and I'm going to figure out ty, and I'm going to figure out tx. So again, pause, use sine and cosine, and figure out your values for ty and tx. All right, hopefully you are back. All right, let's take a look at how you do this. All right, so this is my opposite side. This is my adjacent side. Okay, let me start with the opposite side. So that would be the sine of 30 degrees equals ty over 100 newtons. So I'm going to multiply both sides by 100. I'm going to get 100 sine 30 equals ty. Sine of 30 is a half, so this gives me a ty of 50 newtons. I'm going to do the same thing to figure out tx, except I'm not going to use sine, I'm going to use cosine because it is an adjacent side. So cosine of 30 equals tx over 100 newtons. Multiply both sides by 100 to get it out of the bottom of my fraction. 100 cosine of 30 equals tx. Cosine of 30 is about 0.866, so this will give me 87 newtons for tx. Okay, so this is 87 newtons. All right, now I'm going to apply left equals right, up equals down. Let's start with left and right. Forces to the left equal the forces to the right. Look at your diagram. Pick out the two forces that fit this description. There are only two. All right, what is actually pointing to the left? The force of friction. What is actually pointing to the right? Tx. Now you know one of those. You know Tx. It's 87 newtons. Well, that tells you the value of the friction. It's also 87 newtons. So that makes it easy. Now the other one, the forces pointing up have to equal the forces pointing down. Ask yourself. Now this one, I want you to stop the tape, stop the video, and draw your, tell me what's pointing up, tell me what's pointing down. So pause, write a formula, come back. All right, I'm assuming you're back. What is pointing up? Normal force and Ty. Those are pointing up. What is pointing down? Gravity. Think about it. You know two of these three, right? You know that normal force, well, that one we don't know, plus 50 newtons equals 98.1 newtons. So that means normal force is 98.1 minus the 50. There we go. 48.1 newtons. All right, guys, we will be doing lots more practice in the days to come. And ask me if you've got some questions. Talk to you soon.